Hello everyone! Today we're going to go through a very brief and basic introduction to inorganic elucidation. And in this video, I won't be going through how to write chemical equations, how to balance them, or very specific examples of descriptive chemistry, such as identifying compounds based on their smells and colors. So I wouldn't be going through all of those. However, I will be going through some specific techniques and also things you need to know when you are approaching elucidation problems. So without further ado, let's just dive into the definition of inorganic elucidation. So let me break it down into two parts. For inorganic chemistry, it is the study of elements and compounds, excluding those really complicated carbon stuff that organic chemists deal with instead. As for elucidation, this is basically puzzle solving but for inorganic compounds. And the problems you will be facing in the Olympiads will be like puzzles, and our clues can be descriptive or numerical. As I said just now, descriptive clues include the colors and also the smells of compounds, while numerical clues include percentage by mass or the actual masses or the different yields or molar masses of compounds. So those are the numerical clues. So in this video, I'll be focusing more heavily on how to approach numerical clues rather than giving very specific examples for descriptive clues. And one thing to note is that making inferences from descriptive clues require really strong background knowledge that can only be built up slowly through reading and doing more problems, such as knowing all the group trends or specific elements and what compounds they form, such as compounds of vanadium and compounds of chromium. And even using numerical clues sometimes require chemistry common sense. So for example, when the numerical clue fits two elements, they need to decide which element will make more sense chemically. So if you know a compound will be impossible to form, then of course you need to remove that compound from your consideration and not give that as your final answer. So in my opinion, rather than reading aimlessly, reading those really thick inorganic chemistry textbooks, you should practice using real problems such as those from your national Olympiad or from past ICHO papers. And a good thing about them is that the answers to those are often freely available online. So let's take a look at some considerations that we have in inorganic chemistry. So the first is that the mass of reactants and products must be equal. So that means the mass is conserved. Although you might have heard of something called mass energy equivalence when you're dealing with nuclear chemistry or physics, that is not in the scope of this video, and for the simple purpose of inorganic chemistry, we are just going to ignore that and say that the mass of reactants equals the mass of products. And the second rule is that compounds must be overall neutral. That means they have no overall charge. So if you have something like NaOH, right, sodium hydroxide, then the sodium ion has a +1 charge and the hydroxide ion has a -1 charge. So the charges must balance. So the NaOH as a whole doesn't have a charge. And the third line is more a calculation rather than a rule. So the molar mass or the relative molecular mass of a compound times the amount or the number of moles of that compound will give you the mass of the compound. So for example, if you have hydrogen gas, its molar mass is 2 grams per mole. And if you have 3 moles of hydrogen gas, then you have 2 times 3, which is 6 grams of hydrogen gas. The fourth thing you need to know is that the percentage by mass of X and Y is just equal to the total mass of X and Y divided by the total mass of Y times 100%. So for example, if you take hydrogen chloride as an example, the percentage by mass of hydrogen in HCl is just 1.008 divided by bracket 1.008 plus 35.45. So that's the molar mass of HCl times 100%. So it's you take the mass of the elements or the group of elements divided by the molar mass, and that gives you the percentage by mass. I'll demonstrate how you can use this using an example later on, but for now you can bear these two calculations in mind. And let's now take a look at our first example. So here we are supposed to identify the binary oxide that contains 74.2% by mass of element X. So what is binary oxide, or what are binary compounds? So binary compounds are compounds that contain two unique elements. So in this case, binary oxide simply means that one of those elements is oxygen and the other one is element X. So the first step is always to set up our equation. So since the oxidation state of oxygen is -2, if the oxidation state of element X in this binary oxide is +A, then the oxide can be written as X2OA. Why is this the case? Well, because the compound must be overall neutral or have no overall charge. So if each oxygen contributes -2 charge and there are A oxygens, then you have -2A charges for on the negative side, and you need to balance that by a +2A positive charge. So if each atom of X contributes a +A charge, then you need to have two of those, so it can balance out all the negative charges contributed by the oxygen. So let the relative atomic mass of element X be small x. And with this, we can set up our equation. So 74.2% equals to 2x. So that's the mass of element X inside 1 mole of the compound, divided by 2x plus 16 times A. So this is the molar mass of the compound, because you have 2x atoms in each in a formula of this binary oxide, and you have A oxygens, and each of these oxygens weighs 16 grams per mole. So yeah, that will give you your molar mass. And solving this equation by doing the math, you will get that X equals to 23.01 A. So one thing to note is that you should always put X, which is something that you want to compare against the values on a periodic table. You put that on your left-hand side. And on your right-hand side, you put the ratio you have calculated multiplied by, in this case, it is A. So A can only be integers, right? So you're going to substitute values into A, and you just put A on your right-hand side. So your right-hand side is the side that you want to substitute values in, and your left-hand side is that one single thing that you wish to compare against the values on the periodic table. So you can substitute A equals to 1, A equals to 2, A equals to 3, and so on. And when you substitute A equals to 1, you get that X equals to 23.01, which is quite close to the relative atomic mass of sodium. And because in this case, A equals to 1, so we know the oxidation state of sodium is +1, and that's really reasonable. So here we have found a very reasonable answer, and the answer is just Na2O, or sodium oxide. So after you check whether the numbers match, you need to check whether the element makes sense. So you know sodium oxide is something that really exists, as it should be, because our answers to these inorganic chemistry problems should always be real elements and real compounds. And because of that, you know Na2O is a real compound and it fits all the descriptions in the question. And that's why you know that this is our correct answer, and we can move on to the next example. So another tip that I wish to give is that since the weight percentage, or the percentage by mass, is only given to 3 significant figures, the relative atomic mass only needs to match to 2 or 3 significant figures as well. What does that mean? That means a reasonable match that really makes chemical sense, that you know the compound exists, is more important than finding that perfect match right up until the last decimal place, because here we are doing chemistry, we're not just doing mathematics, and that's why a reasonable match that makes sense is more important than a perfect match that matches exactly. Okay, let's now take a look at our second example. So here let's identify the binary compound with omega S equals to 46.3%. So this omega here simply means percentage by mass. And the S here obviously means sulfur because we're dealing with inorganic compounds here. And again, the first step is to set up the equation. So since the oxidation state of sulfur is -2, well, usually in this kind of binary compounds, if the oxidation state of the other element X is +A, then the oxide can be written as X2SA. So that's similar to our previous example, and I'm not going to repeat how we got that, but it's based on charge neutrality. And let the relative atomic mass of element X be small x. Then using this mass percentage, we can set up our equation. So 46.3% equals to, so that's the mass of sulfur divided by the molar mass of the binary compound. And by solving this equation, we get that X equals to 18.60A. Again, X is something we want to compare against for the values on the periodic table, and A is something that we can substitute in. And since A is likely an integer, we can substitute A equals to 1, 2, and so on, and we find that when A equals to 3, X equals to 55.80, which is close to the relative atomic mass of iron. And just nice, iron 3 makes sense to us because 3 is a common oxidation state of iron, and we know that Fe2S3, this binary compound, truly exists. And that's why we know that this is probably our right answer. And we are going to choose it over all the other values of small x that we have hit on the periodic table. So we know that our answer should be iron 3. Now, having dealt with binary compounds, let me now move on to something slightly more complicated, and that's ternary compounds. So ternary compounds are just compounds that are made up of 3 elements rather than 2. So you have one more than binary compounds. And using ternary compounds, I am going to demonstrate to you how we can use mole ratio to help us elucidate compounds. So in this example, we have 5 grams of ternary compound Y, and it undergoes thermal decomposition in the absence of air. So you only have Y here, you don't have anything else. And that gives you 0.798 grams of carbon dioxide, 0.290 grams of oxygen, and some mass of element X that we don't know. And here we're supposed to identify Y. So the first thing we need to do is to convert all the masses to the number of moles, because masses are not that useful to us if we don't know the amount of the individual substances there are, because the molar mass of carbon dioxide and oxygen are not equal. So if we simply compare the total mass, then that wouldn't supply us with a lot of useful information. So the first step we need to do when we are given all our masses is probably just to convert all the masses into the number of moles. So how do we do that? We just take the total mass divided by the molar mass, and that will give us the number of moles of that substance. So for carbon dioxide, we can take 0.798 divided by its molar mass, which is 44.01, and that gives us 0.01813 moles. We do the same thing for oxygen, and we get 0.00906 moles. So one thing we can note here is that the amount of carbon dioxide is 2 times the amount of oxygen. And that gives us a clue, because such things are so rarely coincidences in inorganic chemistry. So we know that something is sus. And because the ratio of CO2 to O2 is 2:1, we know that when we combine these two, so these two will be combined in this ratio in Y, in compound Y. And when they're combined in this ratio, you do your mass balance, that gives you the carbonate ion. So we know in 5 grams of Y, there are 0.01813 moles of carbonate ions in Y. And using this piece of information, let's now set up an equation which we can solve. So let the relative atomic mass of element X be small x. And because of our charge balance rules, we know that the amount of X to the amount of carbonate ions in Y must be equal to 2:n. Because if the oxidation state of X in Y is plus n, then because the carbonate ion contributes a minus 2 charge each, so we need to balance these two. So X to carbonate ions will just have a mole ratio of 2:m. And so again, because of the conservation of mass, we can find the mass of element X produced in this decomposition. So you start out with 5 grams of compound Y, and you will end up with 5 grams of products in total. So we take 5 grams of total products minus the mass of carbon dioxide minus the mass of oxygen, and that will give us the mass of element X produced. And because of this, we can take the mass of element X divided by its molar mass or divided by its relative atomic mass, and that will give us the number of moles of element X produced. And this will just be equals to the number of carbonate ions that are present in Y multiplied by the ratio of the number of X in Y to the number of carbonate ions in Y. So this is just making use of the ratio and using the math to help us set up this equation. So let me just repeat this since this is very important. So on the left-hand side of this equation, we find the number of moles of X produced by using the mass of X. So the mass of X is 3.912 divided by its molar mass, we find the number of moles. Another way to find the number of moles is to take the mole ratio of X to carbonate and multiply it by the amount of carbonate that is present in the same mass of Y. And using this, we have set up this equation which we can then solve. And solving this, we get X equals to 107.9 m, and m can be any integer, and X is just the value we wish to compare against for the atomic masses on the periodic table. So we find that when n equals to 1, the value of small x is close to the relative atomic mass of silver, and that's why we know that big X is probably silver, and because we know that silver 1 carbonate truly exists, our answer would just be Ag2CO3. Okay, having explained how we can use mole ratios, let's now move on to using clues from description. So how do we know which elements to guess or which compounds that are plausible using clues from the description? So this is a little bit more complicated than the examples from just now, but let's just deal with it. And let's begin. So compound A and compound B both contain element X, but in different mass percentages. So we don't know what element X is, but we know A and B both contains it. So one of them contains 26.2 percentage by mass X, while the other contains only 8.25%. So one of them contains much more X than the other, at least in terms of mass percentages. And we know that 26.2 is roughly 3 times of 8.25, so that's something to bear in mind. So maybe one of them contains other elements that are much heavier, and that's why the percentage by mass of X inside the other compound drops. Or maybe one contains more X atoms than the other. So we will just have to find out which is our case here. And when A and B are dissolved in a stoichiometric mass ratio of approximately 1:3 in water, they undergo an exchange reaction to produce a white precipitate in a solution. So we know that the difference in the percentage by mass is just because of the other elements present in a compound, because 26.2 divided by 8.25 is roughly 3, and our ratio is 1:3. So that just means that one of they probably contain the same number of atoms of X inside each of their formulas, but one of the compounds contains a much heavier element, and that's why the percentage by mass of X is lowered. So let's continue. After the precipitate is isolated, the solution can be evaporated without leaving a residue. Apologies for the typo here. So the sentence is, after the precipitate is isolated, the solution can be evaporated without leaving a residue. And interestingly, when A is heated alone, it also decomposes without leaving a residue. And here we are supposed to identify A and B. So the clue from this description is the biggest clue is no residue after heating, and that's very characteristic of ammonium salts. So you might not know this, but ammonium salts such as ammonium chloride, ammonium nitrate, ammonium carbonate, these decompose without leaving behind a residue. That is, after its decomposition, all of its products are gaseous. So yeah, so this clue basically hints to us that both the solution and A contain ammonium salts. And this is something I've highlighted just now. So 8.25 times 3 is quite close to 26.2. So possibly element X is just nitrogen, and both A and B contain an equal number of nitrogen. This is because we know that both the solution and A contain ammonium salts. So the natural first step for us to take is to either assume that A and B both contain nitrogen, or they both contain hydrogen. But hydrogen, and that would probably be true, but we know that X is probably nitrogen because hydrogen is so light, and so it's very hard to imagine it taking up 26.2% by mass of a compound. So we probably have to guess that X equals to nitrogen first. And to verify our guess, let A, so compound A, be ammonium Y. So Y is the anion, which we don't know. And the percentage by mass of nitrogen is 26.2. So you take 0.262 times the molar mass of the compound. So this is the molar mass of the compound. And that will give you the mass of nitrogen inside the compound. So that's 14.01 times N, where N is the number of nitrogen, and 14.01 is the relative atomic mass of nitrogen. And after solving this equation, you get that Y equals to 35.4 N. And when N equals to 1, the small y will just be equals to 35.4, which is quite close to 35.45, and that's the relative atomic mass of chlorine. So we know that A is possibly NH4Cl, and that really makes sense to us because it is a compound that really exists. So we can call it a day and say that X is nitrogen is verified. However, if you want to be extra safe, we can substitute other values of N. So N equals to 2, where there's no match for the relative atomic mass. And when you substitute N equals to 3, something interesting happens, because the value of small y will be very close to the relative atomic mass of PD, and A would then be NH43PD, which is really weird because that doesn't seem to fit the description elsewhere in the problem. So we are pretty sure that PD isn't an element that we're looking for inside this problem, and so we can safely reject this solution. So let's just move ahead with the X is nitrogen answer, and so we know the relative molecular mass of B will just be equal to the molar mass of nitrogen, the relative atomic mass of nitrogen divided by the weight percentage of nitrogen in X. So we know that there's only one nitrogen atom inside the formula of B because there's only one atom of nitrogen inside the formula of A, and we know these two are in one, and we know the number of oxygen inside the formula of A and B is equal because of this clue here, the 1:3 clue and the ratio of 26.2 to 8.25. So we know that's the case, and it makes our life much simpler. So another thing to note is that since B contains nitrogen, to undergo exchange reaction, the cation in B must not be the same as the cation in A, which we have confirmed is the ammonium ion. So we know that the anion in B probably contains the nitrogen instead of the cation. So the cation in B is something else because nitrogen forms very few cations, and we probably be safer with guessing the anion in B to contain nitrogen instead. And we know plenty of anions which contain nitrogen, such as nitrate and nitrite. And because all these anions also contain oxygen, and we know that nitrogen forms a variety of anions with oxygen, we can move ahead with setting up this equation. So the relative molecular mass of B without nitrogen, that means the mass of everything else in B, is 169.8 minus 14.01, and it gives us 155.8. And because we know that B contains only one nitrogen, we don't need to subtract any more nitrogens from it. Instead, we can just subtract more oxygens from it. So we subtract the molar mass of oxygen away from 155.8 to see if we can hit any element that can be the cation. So subtracting all away, we get 139.8, which doesn't ring a bell for any of the cations. We minus 16, which is the relative atomic mass of oxygen again. We get 123.8, which again doesn't hit anything. And we subtract 16 again, and then we get 107.8. And that's really close to silver. So B will just be silver nitrate. And that makes sense because silver has a plus one charge here, and the NO3 minus has a -1 charge, so the charge balances out. And we know that silver nitrate is a compound that really exists, and with this we can make sense of what is the white precipitate formed. So the white precipitate is just AgCl, so silver chloride, and that also makes sense to us. And so we have verified all our answers, and we know that A and B are just NH4Cl and AgNO3 respectively. So the moral of this story is that the answers are real compounds, so we should start simple and try to find our answer through this very simple and logical train of thought before we move on to something more difficult, which we should only do when this simple way of thinking doesn't yield any results. Okay, finally, let me go through one last example, and this example is super important because in chemistry Olympiads, redox reactions are really common, and there's no way you can avoid them, however complicated they might be. So another thing we need to understand through this example is how we can make use of titration data. And let's take a look at an example. So when elements X and Y are heated together in a 1:1 mole ratio, the main product formed is compound Z. Excess sulfuric acid is added to 0.1 grams of pure Z in a conical flask, producing a toxic gas with a rotten egg smell. Solution in conical flask is treated to remove the toxic gas. 0.01 mole per dm cube KMnO4 solution is added dropwise to the conical flask until the end point. The titration value is 22.75 cm cube, and let's identify Z. So what does this tell us? Well, the first thing we need to do is again convert everything to the number of moles to help us better understand the ratios. So for the potassium permanganate, we can take the volume times the concentration to give us the number of moles. So we take 22.75 cm cube times 0.01 mole per dm cube, and that gives us 0.2275 millimoles. So instead of writing 22.75 over 1,000 to convert cm cubed to dm cubed, we can just add a milli prefix in front of the mole unit, and that will make our life so much easier as we have less things to press in the calculator. And in this reaction, permanganate ions are reduced to Mn2 plus ions. So we know the oxidation state of manganese dropped from 7 plus 7 to plus 2. So we know 5 electrons are transferred to each permanganate ion, and because of this, we can find the overall number of electrons transferred in this titration, and that's 0.2275 times 5, because for each mole of permanganate ions, you need 5 moles of electrons. And that's why we will get the total number of electrons transferred equals to 1.1375 millimoles. Take note that we're still using millimoles as our unit. And next, we can find the amount of Z that has reacted. So that is just the total mass of Z, so that's 0.1 grams, divided by the molar mass of Z, so that's small z, and we get our answer in the units of moles. However, because we have converted everything else into millimoles, we should probably convert this into millimoles as well to avoid confusing ourselves. So our answer will just be 100 over Z millimoles. Then, after having dealt with all these numbers inside the question, let's take a look at the qualitative aspect to understand what exactly is going on in the titration. So, for the rotten egg smell, that is quite characteristic of the hydrogen sulfide gas, and it can be liberated from sulfides by adding a lot of acid. So, for example, if you add HCl into Na2S, then you will produce a lot of H2S and also NaCl. However, this is not something you should try alone because H2S is highly toxic. So in low concentrations, it smells like rotten eggs, and in high concentrations, it kills you. And because of this, we know that either element X or element Y is sulfur, and because the question didn't ask us to specify, or the question didn't specify for us, so we can just let element X be sulfur. And to find the identity of element Y, we can suppose the oxidation state of Y increased by A. So after we remove the toxic H2S gas from the conical flask, we're just left with whatever form of Y there is in a conical flask in the solution. So we are titrating a form of Y against potassium permanganate solution. So the ion of Y got oxidized by the permanganates, and it gets oxidized into something else. So let's suppose that in this oxidation state of Y increased by A. So for example, it might increase from 1 to 2 or 2 to 3. I don't know. We can find out. So we take the number of moles of Y present, and that's 100 over Z millimoles. So because we know X and Y are heated together in 1:1 mole ratio, so we know that the mole ratio of Y to Z is also 1:1. Well, that's probably the case, and because 100 over Z is the number of millimoles of Z present in a conical flask, we know that 100 over Z is also the amount of Y ions present in a conical flask, and multiplied by A because the oxidation state of each of these ions gets increased by A, and that will be equals to 1.1375. So that's the total number of electrons transferred to the permanganate. And because all these electrons must have come from Y, we can set up this equation. In solving it, we get that X equals to 87.91A. And small z is just the relative molecular mass of compound Z. So when we substitute A equals to 1, we take the relative molecular mass of compound Z minus the relative atomic mass of sulfur, because we know there's one sulfur in each formula unit of Z. We get 55.84. and that's quite close to iron. So we know that Z can be iron 2 sulfide, and that really makes sense in the context of this question. And it fits all the other data and all the other descriptions because when you heat iron together with sulfur, you can get FeS. And so we have pretty much verified our answer, and we can just call it a day and write this down as our final answer. And that's all I have in this set of slides. I hope you have learned something. And the important thing is really to keep practicing and keep trying new questions, seeing new compounds, and that will really help you with the exposure and also how also your skill level and the number of techniques and also the number of compounds you know. So that's really going to help in the long term. So I encourage you to try more and also learn more. So I'll see you in the next video. Bye.